we have been differentiating things like this. We can do it now because we know that we multiply by the power, reduce the power by 1, just like we were doing last year with single powers of x. But then we have to multiply, and I'm sort of using that dot notation. I had a bit of a debate with my physicist colleagues in the other group about where the dot goes. I apologise if it doesn't really matter, does it? But there we go, I like to do that. We multiply by what you get when you differentiate the bracket. So in that case, if I was asked to differentiate, the answer would be 4. So that's just 20 of that. So that was the first thing we did last week. And then, on Friday, we learned that we could differentiate e to the x, which is the easiest thing to differentiate because it's the only function which just doesn't change. And therefore, we can say, right, so I can differentiate that because I get that multiplied by what you get when you differentiate, well, this time it's the power, and differentiate that, I get 4, so that's... And it got even more exciting because we then launched into ln x, and we said, right, when you differentiate ln x, and I gave you a brief sort of justification, but nothing more than that, just something to remember, you get 1 over x. And we can say, okay, if you differentiate that, therefore, you get 1 over that multiplied by what you get when you differentiate the brackets. And that's probably best written as this. And we looked on Friday. If you haven't seen the video Friday, then please do, because it looks at a couple of special cases with the logs, ln of x squared, ln of 2x, and we sort of unpick why we get that result, which perhaps is surprising, but maybe shouldn't be so surprising. So I guess with these, I could almost write this in a general form, couldn't I? If we've got y equals e to the power of some function of x, then dy by dx is that multiplied by what you get when you differentiate that. So I'm going to put it in front, could put it afterwards. So it's the differential of the power multiplied by e to the power of that thing unchanged. And for these log ones, if you've got y is equal to the log ln of some function of x, then dy by dx, well, if I just skip to the end, you end up with what you get when you differentiate the bracket over the bracket itself. F dash of x over f of x. So if you're someone that likes sort of standard rules, then those are your rules. But you know, I don't think we need to really think about them because it's not super complicated. So that's where we got to last week. Now, we only differentiated e to the power of x. We didn't differentiate other exponential functions. For example, and that's because it's blooming complicated. All right. The good thing about e to the power of x, the reason we tend to use e when we describe exponential growth, because I can write this in terms of e by replacing 2 with e to the power of something, is because it differentiates easy. But you can differentiate other exponential functions. It just involves a little bit of log jiggery-pokery. So I'm going to go through it now, but it's just one of those things that, yes, it's on the syllabus, it might come up, it's very rare, but I'll go through it now. So if I want to differentiate other exponential functions, so I guess I could call this other exponential functions. I need to do something to the function before I differentiate it. And the thing I have to do is a bit like the idea that if you take x and square it and square root it, you get back to x. Well, if I take that and I do e to the power of ln of that, so this is still the same. what I've done is I've done e to the power of ln of that. And that's like squaring and square rooting. E and ln are inverse. So you basically say this is exactly the same as that. We just, why do that? Why is that? Why, if you take x, would you square it and then square root it and get back to where you started? Well, there's a reason. Because if I look at that bit there, so I'm going to write that bit, and remember the third log rule, I can rewrite that as so that is actually the same as that. And I could write that as ln2 times x. ln2 is a constant. So, 2x, 3x, 4x, ln2 of x. So I'm going to do that over here. So up in this power here, I'm going to say, okay, I've got y equals e to the... I'm going to do that thing there. So I've done that. So what I've... which looks like one of these now. So when I differentiate e to the power of something, the power stays the same. And then I multiply by what I get when I differentiate the power. Well, if I differentiate 3x, I get 3. If I differentiate 7x, I get 7. If I differentiate ln2 times x, I get ln2. Which I'm going to write the other way. Now, do you remember this thing? I'm going to now undo that. So what I've got here is that. So I'm going to rewrite that as ln2 of x is the same as the ln of 2 to the power of x. And this rings a bell. Oh yeah, look. That is 2 to the power of x. E to the ln of 2 to the power of x is 2 to the power of x. So when you differentiate this, you actually end up with this. And if it was 3 to the power of x, you'd end up with ln 3, 3 to the power of x. And if it was 4 to the power of x, you'd end up with ln 4, 4 to the power of x. So you may be I don't know what your capacity for remembering new things is. You may choose to just remember it. And you can, if you get a question like that, there's nothing wrong with just going straight to that if that's something you've remembered. It may be that you go through that process. I don't know. It's pretty rare. Pretty rare. And when on February the 7th, when we get the exam board's published guidance on what the exam's going to look like, I really hope that it's going to be a really specific list, and things like that won't be included. I hope they're going to focus on the core, but we shall see. We shall see. So I only do that as it's quite a neat little trick. My main concern, though, is that we can do these three things. We can differentiate brackets. We can differentiate e to the power of something and the ln of something. That's what I'm really hoping we can do. That's like a little optional added extra. But there's one area of really exciting maths that we haven't differentiated yet. So we've differentiated complicated brackets, we've differentiated e's, we've differentiated logs. So what do you think is going to come next? Someone said it. I can't see it on your masks, but there you go, yeah. We're now going to look at differentiating trig. we haven't differentiated sine, cos, or tan. But working out the gradient of functions that involve sine, cos, and tan, that's really, really important, really useful to a lot of people. Probably not least our friends with the James Webb Space Telescope, because often orbits and things are defined in terms of trigonometry. Anyway, so this is what we're looking at today, differentiating. Now, when we first looked at differentiating, we did differentiation by first principles. And differentiating sine and cos by first principles is on the syllabus. However, I'm going to add that to my relatively short list, but it's getting longer, of things that we'll do if we have time. Okay? And again, I'm hoping that's going to be on the list of things the exam board says, actually, no, we're not going to ask you about that. We're going to focus on the core. So I'm not going to do the differentiation by first principles at the moment. We're going to launch straight into me showing you what you get when you differentiate sine, what you get when you differentiate cos, and what you get when you differentiate tan. I will just give you a small justification. So that's the graph of sine. Okay? Now the first thing I must tell you, as is being the case in other areas, is that we can only differentiate sine, cos, and tan if we're in radians. This only works in radians. So this only works when we are dealing with graphs that look like this. Remember what differentiation does? It's still the same, even though it's more complicated. It gives us a way of getting a formula for the gradient of the curve. And if we work in radians, and if I draw a tangent to the curve at exactly 0 degrees and do the bishop and work out its gradient, you get exactly 1. I'm going to tell you that, okay? The first principles demonstration proves that, which we may well do, but we're not going to do it today. So the gradient of sine at 0 degrees is 1. I'm going to plot that. It's 1. The gradient at pi over 2, 90 degrees, is 0. There's a turning point. So that's 0. So the gradient at this point is 0. The graph of sine, like cos, has a symmetry to it. So if the gradient at this point is plus 1, the gradient at that point is going to be minus 1. And in between these points, the gradient gets smaller. So this is concave. Point of inflection here is concave. But it's not changing in a linear way. So there's sort of a bit of a curve in there. Here we've got a turning point again, so the gradient there is 0. And back here, same as here, we've got a gradient of 1. So if I join those points up and sort of smooth them out a bit, does that curve look familiar at all? It gives us the cos curve. And this is this really lovely result. That when you're working in radians, if you differentiate sine, you get cos. So the gradient of the sine curve is the cos curve. So when I differentiate sine, I get cos. Now, I can do the same with the cos curve. I'm not going to, but it's quite interesting because at this point the cos curve is, gradient of the cos curve is 0. Here it's minus 1, here it's 0, here it's plus 1, then it's 0 again. You actually get a reflected sine curve. So when you differentiate cos, you get minus sine. And that's like minus 1 times sine. If you differentiate minus sine, well, sine becomes cos, so minus 1 times sine will become minus 1 times cos. And when you differentiate cos, you get minus sine. So when you differentiate minus cos, you get plus sine. So you get this beautiful circle. And if I have time, I'm going to 3D print you a little fidget spinner with those things on, a little bearing, because it helps you to remember. So you get this beautiful little circle when you are differentiating sine and cos. They are inextricably related. Of course, tan is always different, isn't it? but it's on the formula sheet if you forget it. When you differentiate tan of x, you get sec squared of x. And I'm not going to go through a proof of that, but you can demonstrate it roughly from the graph by looking at how the gradient of the tan curve changes. But that's on the formula sheet. Most people seem to remember it. So, black for not differentiated, blue for differentiated. And so we can differentiate steadily more complicated things using a similar approach that we were using for e's and logs and the brackets that we've come across in previous lessons. So when I differentiate sin x, I get cos x. And I use the chain rule to differentiate sin 3x. I say, okay, sin 3x becomes cos 3x multiplied by what you get when you differentiate that term, which is 3. Now that's not the cos of 9x, it's the cos of 3x times 3, so that's probably better off written like this. So that's the whole thing gets multiplied by 3. Minus sine becomes minus cos, so minus sine 3x becomes minus cos 3x, multiplied by what you get when you differentiate that. And sine becomes cos, so the sine of 3x plus 4 becomes the cos of 3x plus 4, multiplied by what you get when you differentiate that, which is 3. So we get this sort of one-size-fits-all approach, whether you're differentiating brackets, e's, logs, or trig, that we take the basic differentiation rule and we multiply by whatever the function that we're dealing with is. So we are on page 246, was it? 234. 234. So have a go on page 234 at do it in this order actually, 6 and 8, and then have a look at 5. Just 5 is a little bit more complicated. 6 is quite nice and easy, and then 8 is a bit more complicated than 5. you're going to differentiate it and then just make x equal to pi over 2 and work out the gradient. Did you pick up that that second term becomes positive? Because it's minus cos, which becomes sine. So it becomes plus 4 sine 2x multiplied by what you get when you differentiate brackets. But remember, that's not sine 4x, it's all of that multiplied by 2, so you get that. And then you're just going to make x equal to 5 or 2. And make sure you calculate it in radians. Should get 8 for that first one. First term is 8 and the second term is 0. Please also help both of you getting that correct. Okay, Grace. Is it the plus? When you, is your calculator in radians? Oh yes, it's pi should be up top. That's right. So in 6 you're using dy by dx to work out the gradient at that point, and then you're into your standard y equals mx plus c gradient and point process. So it's only this bit that's new really, isn't it? The rest of it is, you know, old stuff. So you think you should get a gradient of -5? So you get y is -5x plus something. We then substitute the point in, so y is -1 and x is pi. So that means c is 5 pi minus 1. So my final answer, which looks horrible, but you know that's the way it is, -5x plus that, plus 5 pi minus 1. Now, I don't know if any of you have got on to 5 yet. I'd like to have a go at 5 independently, just because it's trig, so it's actually quite nice to, good sort of preparation for Friday anyway, or good practice, because you're going to end up by differentiating, and it's 2 different terms, so I can differentiate that. That just gives me 1, and that, I'll let you work that out. And we want to find the stationary point, turning point, so we're going to ask when that equals 0. And you're going to end up with an equation that says cos 3x equals something, and you've got to solve. X is between 0 and pi, so you'll have to go for 3x, you'll have to go as far as 3 pi. You should find 3 answers. So I'm going to propose that you try that one ahead of next lesson, as your independent study question. I know some of you have got business to think about, but see if you can at the very least differentiate it and get somewhere along the road. A little bit of light relief from all that business revision. But I'd like to move on, if that was okay. The reason I want to move on is that where we go actually now gives us plenty of chance to practice all of the things that we've been looking at. The 4 things really that we've been differentiating: the brackets, the e's, the logs, and now the trig. So any questions about? So have a go at page 234, question 5. Some of you will have started it. Mouse?
Thank you, sir. I've already been looking all over them.
I would have brought it out.
Oh, no worries, sir.
Okay, so can we play a little bit of spot the difference before we move on to the next step then? Okay. Spot the difference. One of these I can differentiate at the moment. This one. Because when you have a function made up of terms being added or subtracted, you can just differentiate the separate terms individually. So that would give me 2x plus 3 cos 3x. This I cannot yet differentiate. This is a product of 2 separate things that I can differentiate, but the fact they're multiplied means that it's more complicated. And the good news is that there is a way of differentiating things like this, and it is called, rather unimaginatively, the product rule. So that's where we're going next, to the product rule. The product rule allows you to differentiate 2 things multiplied together, as long as you know how to differentiate the 2 things on their own. And it starts by saying, okay, what are the 2 things, the 2 separate things? Well, in this case, it's x squared and sine of 3x. First thing you do is you differentiate them separately. And I always like to set it up in a little grid. This is Humphrey, my now long retired colleague, would call these her windows. So you put the 2 things that are multiplied together in your function there, and then underneath you put the 2 things which are you get when you differentiate them separately. So if you fill in your windows. And because it's a product, two things multiplied together, the order doesn't matter. You know, when you multiply two things together, it doesn't matter which way around you do them. And then, I've used the wrong colour, haven't I? Sorry, that should be black. Oh well, that's going to confuse me. Sine becomes cos, so 3 cos. And then all you do is, and the derivation of this, not on the syllabus, I'm sure there are YouTube videos explaining it, is you multiply those two things together and add them to those two things multiplied together. So those two things multiplied together, so this is how, we're not talking about that, I can already differentiate that, but for this, dy by dx, are those two things multiplied together, and it's, you know, choose the way it makes sense to write them. I'm going to write that as 2x times the sine of 3x. And then you add those two things multiplied together. And that, I've got x squared times 3 cos, so I'm going to write that as 3x squared cos 3x. You don't need the dot, actually, no. So it's those two things multiplied together, added to those two things multiplied together. Now, for those of you who like a rule, you could write the rule in one of two ways. You could say, okay, so if we've got a function made up of two separate things being multiplied together, then the product rule tells us that the differential is that one multiplied by what you get when you differentiate that one, plus that one multiplied by what you get when you differentiate the other one. You could write it like that if you wish. You may feel you don't need to write it at all because it's just, you know, do it with the windows. When I was at school, back in the days, we used to say, right, it's when you've got two things multiplied together, we'll call them u and v. So it's v multiplied by what you get when you differentiate x, added to u multiplied by what you get when you differentiate v. And I remember that because in the old days, didn't have laptops, didn't have tablets. Our school had 3 computers, and they were all in one room, and they were really big, and the monitors were sort of this size, and they went back about a mile, and the text on them was green. And they were called visual display units. So I always remembered this as v du by dx, v du, visual display unit. That's how I remember it. Of course, that means absolutely nothing to you, so there you go. I can't really get to use that. So I use Mrs. Humphrey's windows, I think. Put the two things that make up the original function there, differentiate them separately, and then it's just those two things multiplied together. It's not on the formula sheet. It's not a complicated thing to remember, though, is it? And so the product rule gives us answers which, they've always got things in common. So there's plenty of scope potentially for factorising. Now I'm not going to factorise that, but you know, you could perhaps see in a question that asked for turning points, when does it equal 0, I could pull out an x, and you know, there's scope there to sort of, you know, to sort of fashion quite a nice algebra question. Anyway, we won't worry about that now. We'll just do a little bit of practice of using the product rule. So can I get you to differentiate these things for me? So set those things up in your windows, differentiate them separately, and notice how, you know, this gives us a chance to practice the things that we've been doing, so it's all good. And see if you can work out what dy by dx is. user windows?
Briefly, you've done this one.
Does he do?
Yeah.
Right. Doesn't matter which way around you write, that. But I think if you were going to put cos x e to the 2x, you'd have to make clear that e to the 2x isn't part of the angle, so you might have to use some brackets there. And I know I've been using dots. You can dispense with the dots or use them as you wish. I do think with the second one, I would simplify it like, this times this is probably best written like this. Happy with that? So 1 over x times that is the same as that over x. Think of it as a fraction multiplication sum of this being over 1. And then the second term, I'd probably write should we just dip our toe into the whole factorisation thing? So here, both terms have got an e to the 2x in. So I could write that as e to the 2x times 2 sine x plus cos x. And if I was looking for turning points, I would then be able to say, right, well, it's when that equals 0. That never equals 0. And when that equals 0, which would give me an expression in tan. And here, slightly more nasty one, but I could take out a 3x plus 4 squared, which would leave me, well, this I'd have to multiply by that, and then Now, you know, I don't want to confuse you. If you were quite happy sitting there and you're thinking, well, I have no idea what's happened there, then for now that's fine. So, you know, using the product rule to get to that point is fine. But there is definitely potential for factorising, and that often crops up in questions when we are asked to then go on and do something with it. Sorry if I get this out of the way. So let's just do a quick question to finish with that practices using the product rule. Now you could argue that actually for the x minus 2 squared, it might be quicker to multiply that out and then multiply it by that. So you actually end up with a cubic, which you could differentiate separately. You could argue that, but that's no fun, is it? Let's use the product rule. You multiply that by like a bracket, it's not too bad at all. Those at home, this is page 242. 242. So I'm going to do this like a bracket. Multiply by the power, reduce the power by 1, then multiply by what you get when you differentiate the bracket, which is just 1, so actually it's nice and easy. Every good episode of EastEnders, we have run out of time, so we're going to leave that one on a cliffhanger. You may feel, I mean, you've got one to already do for the end of it, you may want to have a little look at that, but we'll, once we've worked through that trig example, we'll pick up where we left off with this one, looking at how we can work out the turning points.